It's recording. So, welcome, Vinay. Thanks for coming in to speak about your honors project with Peter Kim. Okay, and you'll be giving a talk on how does the evolution on monogamy depend on life history, a mathematical model. Okay, floor is yours.
All right. Hi, everyone. It's really great to be back at uni. I'm honestly really thrilled and excited to be presenting to you all. It's actually just really good to see people back in Carswell after a year of virtual screens and COVID. It's honestly just great. Okay, so let me start my talk with a question. What does it mean for us to be human? Now, if you're interested in literature or philosophy, you might have several different opinions on this, but this is a mathematical biology talk, so we're going to stick with the biological standpoint. So from a biological perspective, we humans are distinct from our closest living relatives, the great apes, in three main ways. First of all, our large brain sizes, so we're literally big brain. Our long postmenopausal or post-fertile lifespans. And most surprisingly is our tendency towards monogamy or pair bonding. And this was the problem that I worked on during my thesis. So here's the problem. On the left, you've got a pair of macaws. They're a type of bird, and like most birds, they are largely monogamous or pair bonding. And what that means is that they will mate with one partner for an extended period of time. Now on the right, you've got a chimpanzee. And as cute and as sweet as this creature is, it is not monogamous. In fact, chimpanzees are largely multiple mating, which means they simply mate with whoever is available. They're promiscuous. Now we humans, we're very similar to the chimps and the great apes of the world, but like the birds, we're also largely monogamous. Or at least we were until Tinder came along. But seriously, the evolution of monogamy is one of the reasons why institutions like marriage, family, kind of pervade the fabric of our society today. Now, the biological evidence indicates that this kind of transition happened about 2 million years ago, in like the early ancestors of chimps and humans. But that still leaves the question, why do we pair bond when our closest living relatives do not? Well, it turns out that this question is kind of misguided. We pair bonded, or we became monogamous because it was in our interest to do so. As Darwin would say, the most adaptable species survives. So we pair bonded because it was imperative to do so in order to ensure our continuing survival as a species. But that's not really a satisfying answer. And when you don't have a satisfying answer in science, you reframe the question. So a more appropriate question to ask is, what circumstances promulgate the evolution of pair bonding? And in fact, this is a mathematically open question. There's actually been a fair number of papers on this topic. The first big breakthrough on this was by Hawkes, Rogers, and Charnock in 1995. And previously it was thought that kind of parental care was sufficient to drive the evolution from promiscuity to monogamy. So the idea being that if a dad could care for their child, it was enough of an incentive for that dad to shift their strategy from multiple mating to monogamy or pair bonding. What Hawkes, Rogers, and Charnock counterintuitively showed using game theory was in fact this is not the case, and that the effect of mating competition is much larger than the effect of parental care in shifting the male strategies. So you can see this results in evolutionary equilibria with very little male care. So lots of points are clustered towards the end, which represents the multiple mating. So clearly, our male ancestors 2 million years ago may not have been the greatest parents. In fact, they kind of liked stealing other people's kids. So this is followed by a paper by Schuck and Bell. And what they did was they showed that pair bonding could evolve under conditions of male bias sex ratio. So what do I mean by that? What I mean is that if the number of fertile males is larger than the number of fertile females, it creates a condition of partner scarcity. And that tends to favor guarding strategies over promiscuous ones. And they used a Markov chain model to actually show that the evolutionary trajectories converge on mate guarding. Building on these results, Sarah Liu, Kristen Hawkes, and Peter Kim essentially showed that as the sex ratio shifts from female bias, meaning less than 1, to male bias, larger than 1, pair bonding becomes the dominant strategy, and the proportion of multiple maters tends to go down. But there's a kind of a fundamental problem here in that the sex ratio is not really a fundamental biological object. I mean, you can't just go up to a population and say, let's set your sex ratio to be 0.95 or something, right? So the sex ratio depends on several biological parameters, including mortality, including maturation, including the rate which dependents and children die, all of these sorts of things, mating, and several things that don't begin with an N. So in order to investigate the influence of these kind of life history parameters, Daniel Rose, Kristen Hawkes, and Peter Kim from our mathematical biology group in the applied math department here, we basically, they started to understand how each parameter could try and like shift the evolution. So what they were able to do successfully was understand which life history parameters were important, but what they weren't able to do was essentially determine the entire evolutionary behavior across the entire space of life history parameters. So imagine that each parameter is is some number, and you have a space which is like R something, and you want to know how the evolutionary behavior depends on that space, or how it's clustered in that space. And what they weren't able to figure that out, and that was my goal. And the reason why this is important is because we want to know what circumstances biologically could have led to the evolution of monogamy, and because it also sheds light on certain anthropological theories. We can evaluate those theories in light of our model. So in order to do this, I broke it down into 4 not very easy steps. So the first is to develop a mathematical model that is simple enough to analyze the techniques from dynamical systems, while also being complicated enough to actually model all of the kind of life history parameters that are important. And then from that, we can derive conditions in the form of inequalities where pair bonding is going to supersede multiple mating as the optimal allocation of male reproductive effort, and then see how this lines up or maybe doesn't line up with certain anthropological theories for how this actually happens. And of course, we can generalize the model to further circumstances like for partial differential equations and things like that. Okay, so the basic rule of mathematical life is that when the universe hands you a hard problem, you make a problem easier and hope that the easy problem is close enough to the hard version that the universe is not going to object. Right? So in this vein, we propose a few assumptions to make the problem a little bit easier. So first of all, we assume that all the males either follow completely monogamous strategies or multiple mating strategies. And the reason why we can do that is, let's think about kind of a mixed strategy. Let's say 30% multiple mating, 70% pair bonding or monogamy, right? You're doing pair bonding 70% of the time. So what you can do is interpret this kind of mixed strategy as a kind of coexistence solution, where all males where 30% of the males are multiple mating and 70% of them are pair bonding. So if each person follows a mixed strategy, you can interpret that as a coexistence solution for everyone. And we can also assume that children inherit the strategies of their dads. I mean, it's kind of hard to tell. There are a lot of variables that are influencing the child's mating strategy, but it's reasonable to assume that parental influence tends to play quite a large role. We also neglect any cultural factors, so we assume that ancient human societies 2 million years ago are not like online dating sites. Also, that the life history processes should occur at age-independent rates. So we assume, for example, that fertility loss happens at a constant rate until menopause, when you don't have fertility loss at all. All right? And finally, that the total population of males and females is constant. So if you've heard of the logistic model, you know that when a population is constrained by resources, they tend to settle in on a stable equilibrium where they're not growing dramatically or they're not declining. So for example, yeah, they're not declining. So we can assume that the population isn't growing or declining and that the only thing that is happening is transfers between the strategies. Okay, so now we've essentially assumed what we need to assume, we can now start to develop our mathematical model. So in order to do that, we break down the population into 5 separate compartments, and the relationships between those compartments define a dynamical system, or a system of ordinary differential equations in this case, which we can actually analyze. So the compartments that we're looking at are guarding males, pairs of guarding males and free females, multiple mating males, and the females that are caring for offspring of multiple mating males. That's a handful. Like actually, if you say it fast, that's really hard to say. All right, so now let's look at this diagram a little bit more closely. So what's going on here? So we'll start with the mating transition. So a guarding male is essentially a male who has a pair bonding or monogamous strategy, but is not paired yet. They are mating with free females at some mating rate row, and they're forming pairs of guarding males and free females. In addition, we have multiple mating males that are mating with free females, and the females are getting transferred to this population in orange, females that are caring for the offspring of multiple mating males. We can also define the process of maturation. Maturation is kind of the opposite of mating, because with mating, you have males and females mating, forming pairs, having children, and with maturation, you have children maturing to adulthood and joining these populations. So the idea is that the pairs of guarding males and females have children, and these children, because they inherit the strategies of their fathers, can either become males who follow monogamous strategies, so guarding males, or free females. Now, we assume that the maturation happens at some rate b, which we can estimate, and that the probability of becoming male or female is a half, right? Because you're equally likely to be male or female. Similarly, we have children of these multiple mating males and free females who are going back into either the free female population or the multiple mating population. Now, you might ask why this term here is 3/2b and not half b. And that accounts for single parents, who essentially, once their child has matured, single females, can actually go back into the free female population, which, so there's an extra b worth of females that is going back into the free female population. We can then incorporate female fertility loss. So here, what's going to happen with that is that each female is going to lose their fertility at some rate omega. And, well, where do they go? The idea is that they're transferred into a post-fertile female population that we call X. So every time a female loses fertility, they're transferred from any of these compartments into the compartment X, after which they simply die. And finally, we can also include child mortality. And the idea of child mortality is that when a child dies, the females get freed and can go back into the free female population. Okay, so these are actually the equations that represent in math those diagrams that we just covered. And I won't go through these equations term by term, but I will tell you a few things. So first of all of these half B terms over here represent maturation, as you've seen in the diagrams. The omega terms represent female fertility loss. These delta bar terms represent child mortality, and these rho terms represent mating. The mating occurs at a frequency-dependent mating rate. It's a concept that's taken from infectious diseases, where we actually assume that the mating is proportional to the number of females and the proportion of males with a particular strategy. This turns out to actually be useful in infectious diseases for modeling diseases with kind of slow rates of transmission, for example, STDs, as opposed to, say, COVID. Now, you might notice this extra term over here, this mu of t. This is a little bit weird because we haven't actually talked about it. But what it comes from is our assumption earlier that the population stays constant. And what this is a density-dependent death rate that is designed to reduce the population in such a way that it stays constant all the time. So there is only transfers between the strategies rather than population growth or the population just declining to zero. So we can actually study this, the system mathematically. Right, so now this is the juicy mathematical part. So we have here 6 ordinary differential equations. And when you have these sorts of nonlinear ordinary differential equations, it's extremely difficult to solve analytically. In fact, you usually cannot solve these analytically. So what people do is that they analyze equilibria, so the constant solutions that exist for all time, constant solutions for all time, and that they don't grow. And they analyze these equilibria for stability. And why do they analyze for stability? So stability is really important because it means that neighboring trajectories, or if you start somewhere close to that point, you converge in on that point. And that's really important because that indicates whether a strategy, in our case, for example, pair bonding or multiple mating, is dominant, right? Because if you have some initial conditions and you converge in on a stable equilibrium point, what you're doing is converging on some strategy, for example, pair bonding or multiple mating or coexistence, etc. So our first step is to reduce our system of equations from 6 equations to 4. And we can do that because the total number of males and females are constants. We can write some variables in terms of the others. So we now only have 4 equations to deal with. That's mildly less stressful to deal with than 6. We can then do what's called non-dimensionalization. So writing these things in terms of implicit parameters. So we define 3 new implicit parameters. The implicit parameters are kappa, gamma, and delta. So kappa is the mating rate divided by the maturation rate. Gamma is the fertility loss rate divided by the maturation rate. And delta is the child mortality rate divided by the maturation rate. And what that allows us to do is now we have 3 parameters to study instead of 4. Okay, so that helps us mildly as well. And it turns out that this is important because the parameter space now becomes 3-dimensional, which is actually possible to visualize instead of 4, which is a little bit harder. Okay. Now, once we've done this, we can analyze our system of equilibria. We find 4 types of equilibria. We have stable equilibria where pair bonding prevails. So you can see this blue line. This is where the fraction of pair bonders is really high. The fraction of multiple maters, M, goes to 0. So this is a pure monogamous equilibrium. Similarly, we also have pure multiple mating equilibria. So where M goes to 1, M is really high, P goes to 0, which means that we have pure multiple mating, pure promiscuity. All males are promiscuous. We can also have stable equilibria where the strategies coexist. What that means is that both of the strategies exist for all time and neither can outcompete the other. Neither strategy can send the other strategy to 0, which means that nobody does that strategy. Okay? And of course, we have population extinction that happens for some particular parameters. All right, so in order to actually analyze this for stability, what we do is, let's start with the hypothetical case where we set gamma and delta to 0. So we analyze this in the absence of fertility and in the absence of mortality. And in this case, the answer is very simple. Between 0 and say approximately 0.71, we have pure mate guarding. Between 0.71 and like 1.6, we have coexistence, and otherwise we have multiple mating. Is it realistic? Absolutely not. Humans have a kappa value of about 12, right? They have a mating rate of about, say, 3, a maturation rate of about 1/4, divide 3 by 1/4, and you get 12, and we are way out here. So why is this wrong? It's because we simply haven't introduced enough parameters yet. So what happens when we scale it up to 2 parameters? So now we do it in the absence of mortality, and we have mating and fertility. Now it becomes more interesting. Okay, so we have these 2 axes. One is the kappa axis, which is the mating divided by the maturation rate, and the gamma axis, the fertility per maturation rate. And we essentially separated the entire parameter space into 3 regions: multiple mating, coexistence, and pair bonding. Right? And these regions are separated by these 2 curves that we call alpha of kappa and beta of kappa. And in fact, we were able to find exact expressions for alpha and beta. And despite these rather nasty expressions, they have nice properties. So for example, we can prove, obviously I won't present the proofs here, but we can prove that, I know, it's an exercise for the reader, but you can prove that alpha of kappa is an increasing function, and it's the same with beta, and that they converge to the same limit, which means that the region of coexistence is actually getting smaller and smaller. Okay? So while these curves are ugly, they have very nice properties. Now, what about the 3-dimensional version? So when we have 3 parameters, our curves become surfaces. So this is the 3-dimensional version of the curve alpha. Okay, it's now a surface, or this is the region under the surface. And so in the shaded region, we get multiple mating, and above the shaded region, we get coexistence. And in fact, with a lot of work, it is possible to find this rather nasty expression for alpha as a function of both the mating rate and the mortality rate. So you can find fertility as a function of mating and mortality, and it gives us a boundary saying that when we're below this surface, we get multiple mating, and when we're above the surface, we get coexistence. And we can do the same thing with beta. And in fact, we can also prove again that the partial derivatives of alpha with respect to kappa is always positive for any kappa and delta bigger than 0. And the partial derivative of kappa with respect to delta is always negative when kappa and delta are positive. So what does all of that spiel mean? Essentially what it means is that as you increase the mating rate, you shift towards multiple mating strategies because the partial derivative is positive. And as you increase your mortality rate, you shift towards your pair bonding or coexistence strategies because the partial derivative of that surface, which defines the boundary between the strategies, is negative. Okay, so what does this all mean biologically? Well, first of all, we see that the conditions for pair bonding include reasonably slow mating rate, a fairly large omega, meaning a fair amount of fertility loss, and child mortality. And these provide sufficient conditions for humans to be able to evolve towards pair bonding. And in fact, we tested this model on data from humans and chimps are down here in the multiple mating region, while humans are somewhere above in this coexistence region. And in fact, about 70% of humans will pair bond under this model. Furthermore, we know that now that increasing child mortality shifts the curves downwards, or shifts the surface downwards, because its partial derivative is less than 0, and so it favors pair bonding strategies, while increasing mating drives the population to multiple mating. Now, what's very interesting is, we talked about the coexistence region also shrinking, and that also holds in the 3-dimensional version of the problem with the surfaces converging in on each other too. Now, what is very interesting biologically is that what happens when you increase the maturation rate? Well, it turns out that the effect of this is highly nonlinear. Let me explain why. So let me go back to these curves. We notice that the axes are in terms of the maturation rate. So kappa is in terms of the maturation rate, and gamma is also in terms of the maturation rate. So when I change B, what's happening is we're going diagonally upwards or diagonally downwards. And if we're somewhere here, we can go from coexistence into multiple mating. But if we're over here, we can go from multiple mating to coexistence. So in fact, where we want to go depends on where we are. So the phenomenon is very nonlinear. Now, why is this important? It turns out that there's this evolutionary theory called the grandmother hypothesis. And it says that by increasing, that grandmothers help to support children while the parents were out hunting. And what that does is that it affects the value of B. And that could have led to pair bonding. That's the current anthropological explanation of how this works. But under this model, it kind of shows that, well, it's not as clear cut as that. Sometimes that strategy can actually work, and at other times it can't. And it really depends on exactly where you are in this diagram. So it turns out that the grandmother hypothesis is not necessarily as clear-cut as we thought it was. Okay, so we essentially have developed models that are actually simple enough to actually analyze and conclude and understand not only mathematically, but also biologically. We were able to actually prove things mathematically, but also understand what their implications were and evaluate anthropological theories like the grandmother hypothesis in light of our model. So our next steps, which are actually in my honors thesis, are about including male fertility and generalizing to longevity, so where we have 4 parameters instead of 3 and our space is 4-dimensional, and generalizing to age-structured models. So in that case, we have to include partial differential equations instead of ordinary differential equations, because now we're expressing the solutions in terms of time and age rather than just time. So this is obviously a little bit harder, and we have to sacrifice the neat exact results, which I showed you, for approximations and numerical solutions. Okay, I'm going to end with this quote from Darwin, and he essentially says here that mathematics is like another sense, and indeed it is. Maths is an extension of our common sense by other means. And I think Darwin would have been really pleased to know that the problems that he worked so hard on, the problems of evolution, are now being tackled by mathematics, are now being used, and this extra sense is now being used to tackle these sorts of problems. All right, thank you so much. Questions? Feel free to just speak up. No hands, no nothing, just talk. No questions, come on, guys. Anything you were curious about? Biologically, mathematically, what the structure of the solutions looks like, how the biology works, and anything. Literally ask it. There are no stupid questions.
I know, that was when you had 3D service.
Yep.
So when they went from the multiple mating to coexistence, and then so how before with the coexistence, kind of shriveled out. It was kind of just a gap between pair bonding and multiple mating. What's the coexistence pair bonding gap?
It's pretty similar. So in one direction, it shrivels out, and in the kappa direction. In the gamma direction, it's a little bit more solid. But yes, in the kappa direction, you can show that it shrivels out.
There's factors like IVF decrease the fertility rate.
As in decreasing the fertility rate?
Like decreasing the
Sorry, could you say the question again?
So if you introduce more factors to reduce fertility rates, like for example IVF, what effects would that have?
Well, it's difficult to tell because IVF is a very modern technology, and implemented in ancient hunter-gatherers, it would be a little hard to kind of understand. But let's assume we could somehow artificially decrease fertility, just assume this happened, right? So what's going to happen is that we're also decreasing gamma, which is the fertility loss per maturation rate, which means that we shift down on our diagram. So we're going from maybe over here down towards multiple mating. And the point is that with chimpanzees, they don't experience the same sort of female fertility loss that we do. They're actually fertile for their entire lives, whereas we experience menopause. Okay, we stop, our fertility stops after a certain age, and we live longer than our fertility. And that's one of the reasons why chimpanzees are somewhere over here and we are up there. Right, so that would probably be the answer to your question.
So if I'm understanding correctly, we kind of say so humans just happen to have these traits, right? And then these are the best strategies for certain rates we have.
Yes.
do we have like social menopause and then
So there's a lot of research on it. So one of the reasons, or one of the proposed theories is grandmothering. So the idea is that menopause is an evolutionary idea, and that somehow we evolved the trait of losing fertility so that our grandmothers could help us, and therefore that helped us to hunt so we could get more food so we could survive. Another theory is the hunting hypothesis, which is kind of the opposite, that it worked the opposite way around. So first we evolved monogamy, and then menopause was like a consequence of that. The short answer is that the anthropologists are trying to figure it out, and that they collect a lot of data from chimpanzees and other apes, and also from human hunter-gathering societies. There are not that many of them now, but in fact there are actually a few. Some in like in Africa, some in other populations, some in like Borneo and Indonesia and things. So they actually go out and study these things. I know it seems weird that when working on a chair and using a computer and a paper and do maths, it seems weird that people actually go out into the field and study these things for years and years and years and collect all this data and try and understand it. But yes, they do, and that is essentially what they're trying to figure out. What theory is it that allowed us to have these rates? And it's an open question in anthropology. No one yet really knows the answer. It's a very good question.
So like, if I think that they're somehow dependent on each other, like these equations would be like a lot more.
It would be much
Yeah,
harder.
but if we're assuming like they're somehow independent, so we just like apply it, like, okay, yeah, well, that happens, and then apply these, and then we get like the dominant strategy outcome.
Yes. So obviously there's kind of an implicit assumption here that the parameters or the life history process, not really the parameters, the actual processes are kind of independent from each other. And it kind of makes sense. For example, you wouldn't expect mating and death to be to be like technically too correlated. But at the same time, there is some level of correlation. And it's part of the reason why the solutions don't depend explicitly on like the explicit parameters like fertility, maturation, and so forth, but they depend on these implicit definitions like mating divided by maturation or fertility divided by maturation, right? It's that is kind of part of the reason like the parameters are somewhat related, but the strategies depend implicitly on combinations of the parameters rather than the parameters themselves. All right, I think I'll stop here, but you're free to ask me as many questions as you want after the session. Thank you all so much.